Welcome. So, in this video we will talk about voltmeters. Okay. Now, we have seen previously that PMMC, electrodynamic and MI, moving iron, they measure currents. They measure current directly, in a sense that if we apply a current across the coils of these meters, the pointer is deflected. An electrostatic instrument this measures voltage. Okay. So, particularly electrostatic instruments cannot be used for say DC current measurement directly as it is, because it is made up of a set of two parallel plates. So, it is a parallel plate capacitor, and if you apply voltage between these two, a DC voltage between these two across these two plates, no current flows at all. So, it is sensitive to voltage, but no current can flow through this meter. So, we cannot measure current directly. We can measure it indirectly, but not directly. But electrostatic instruments are not generally used much. This is used only for some high voltage applications mainly. And PMMC, electrodynamic, MI, these are the most common type of instruments which are used most frequently. But they are current sensitive instruments. But can we not measure voltage with them? Yes, we can, using Ohm's law. How? Because say if I have this meter which is a say PMMC or electrodynamic or MI, if I apply a voltage V across this, okay, so what will be the current through this meter? This current I will be V divided by Rm. What is Rm? Rm is the coil resistance or meter resistance or internal resistance. Now, if we know the value of Rm, the pointer will of course indicate the value of I, because this type of instruments in their pointer always indicate the value of the current, and if I know the value of this resistance Rm, then I can always find V is equal to, from this, I times Rm. If Rm is known, and I is observed. So, this is indicated by the position of the pointer, then V can be found. Okay. If I know the value of Rm, then I can compute the value of V. So, I can mark the scale of the instrument in terms of the voltage and instead of the value of the current. Okay. So, using Ohm's law, we can measure any voltage using this type of instruments. That's very easy. Now, the question is, what should be the or how should I mark this scale? Okay. So, if I have a PMMC meter, say if I have a PMMC meter with full scale deflection current, say equal to 10 milliampere, and say the coil resistance is say 100 ohm. Okay, so that means the pointer goes to extreme right when the current is 10 milliampere. So this position indicates 10 milliampere. This is 0 ampere. Okay, now if I apply a voltage across this meter, which is say V equals say this V is equal to 1 volt. Okay, so if I apply 1 volt across this meter, then how much current will flow? Then the current that will flow is 1 volt divided by the meter resistance, which is 100 ohm. So this will be equal to 10 milliampere. So that means the pointer will go to the extreme right, and so this position I can mark as 1 volt instead of 10 milliampere, because when I apply 1 volt across this meter, then the pointer goes to the extreme right. So instead of writing it as in terms of current, I can also write this position as 1 volt. Okay. Now similarly, if I apply say 0.5 volt, okay, so if I apply 0.5 volt, then the current that will flow here is, this will be 0.5 volt divided by 100 ohm. So this will come out to be 5 milliampere. So the pointer will be here at the center. Okay, so the center point, I can therefore mark it as 0.5 volt. Instead of writing it in terms of current like 5 milliampere, I can write it as 0.5 volt. So this way I can get a voltmeter. Now the next question is, if I want to change the range of the measurement, how can I do that? Basically, I have to change the resistance of the meter. Okay, so suppose, so now range changing. Suppose I want to measure up to 10 volt, voltage. Okay, so then what can I do? What I will do is this. So I will. So this is my meter. It has an resistance of 100 ohm. I will connect some series resistance. Okay, call it R S, and I will apply the voltage, the 10 volt voltage which I want to measure across these two terminals. So here I will apply 10 volt. Now what I want, when this voltage is 10 volt, I want the pointer to go to the extreme right position. That means full scale deflection current should flow through the meter. So we want when V is equal to 10 volt, FSD current should flow through the meter. Okay. So, to achieve this, what should be the value of Rs? Okay. So, now we know voltage is 10 volt. So, this is 10 volt and we want this current to be FSD current, full scale deflection current, which is given as, so FSD for this meter is, so let us take the previous example only, 10 milliampere. Okay. So, this current is 10 milliampere. Okay. So, the resistance, total resistance of the circuit should be, so which is Rm plus Rs. So, this is the total resistance. Then this should be given by 10 volt divided by this current 10 milliampere. This will come out to be 1 kilo ohm or 1000 ohm. Now, therefore, Rs should be 1 kilo ohm minus Rm. Rm is known to be 100 ohm. So, we can write 1000 ohm minus 100 ohm. This will be 900 ohm. So, if we connect a 900 ohm resistance, then this arrangement this meter together with this resistance will become a 10 volt voltmeter. Okay. So, this is how you can alter the range or choose the range of a voltmeter that you want to make. Now, this resistance is sometimes called the multiplier resistance. The series resistance is called multiplier resistance. Okay. So, let me just write the name. This is multiplier resistance. Okay. Okay. Now, let's ask. Okay. Let's make, say, multi-range. Let's make multi-range voltmeters. Okay. So, we have a PMMC meter with FSD equals 10 milliampere. This is my favorite number, 10 milliampere, and say 100 ohm Rm equals 100 ohm. Okay. And we want to make a multi-range voltmeter with ranges, say 1 volt, that means 0 to 1 volt, then 0 to 10 volt, and then say 0 to 100 volt. So, this is what you want to make. How can we do that? So, basically we need 3 different values of the multiplier or series resistance. So, this is my meter and I will connect, say, a multiplier resistance. So, this is the meter with FSD 10 milliampere, meter resistance 100 ohm, and we will connect some resistance to get the desired range. Okay. But now, to get 3 different ranges, we need the provision to connect different multiplier resistances like this. So, 1, 2 and 3, because we have 3 resistances. And then let me take a switch. This switch can connect to either this or this or this, and this is the final two input terminals where we apply the voltage. Okay, so this entire thing is inside the multi-range meter. Okay, now let's find out what should be the values of these three resistances. Okay, say we want the ranges to be say this is 1 volt range, this is 10 volt range, and this is 100 volt range. Okay, so let's compute the values of these resistances. Call this R1, R2, R3. So what will be the value of R3? Okay, so let's calculate. So now R3 and R3 plus Rm. Okay, this is the okay, let me first write for, so let me call this as position P1, P2 and P3. Okay, so let me write for position say 3, okay, or P3. Okay, so when we have 100 volt applied across these two terminals, we want the pointer to go to the extreme right. That means FSD current should flow through this meter. Okay, so for position 3, voltage will be V will be equal to, so the voltage that we will apply across these two terminals will be equal to 100 volt, and the current I will of course be at that instant 10 milliampere. So therefore, the total resistance Rm plus R3, this should be this V by I 100 volt by 10 milliampere, and this will come out to be 10 kilo ohm. Okay, and therefore, now Rm is 100 ohm. Okay, so therefore R3 will be 10k minus 10 kilo ohm minus 100 ohm. So this will be this is like 0.1, so this will be 9.9 kilo ohm. Okay. Now similarly for position P2, we want when this voltage applied is 10 volt, full scale deflection current should flow. So here V will be 10 volt, and at that moment the current that should flow, so this current is I, and let me call this voltage, so I am calling this voltage as V, this is V. Okay, so then now V is 10 volt, I should be 10 milliampere, so that means Rm plus R3, this should be 10 volt divided by 10 milliampere, which means 1 kilo ohm. This will imply R3 equals 1 kilo ohm minus Rm, which is 100 ohm. So this will be 0.9 kilo ohm. And similarly for position P1, V applied voltage should be 1 volt, current is once again 10 milliampere. So Rm plus R3, this will be 1 volt divided by 10 milliampere. So this is 0.1 K or 100 ohm. Okay, so now this will imply R3 is equal to 100 ohm minus 100 ohm Rm. Rm itself is 100 ohm, so R3 should be 0. Okay. So, if R3, sorry, this is not R3, this is R1. This is R1. Here also it is R, okay, here it is 2. So, this is 2, this is 2, this is 1, this is 1, right? Yes, okay. So, then R1 should be 0. So, let us put the value. R3 should be 9.9 kilo ohm, R2 is 0.9 kilo ohm, R1 is equal to 0 ohm. 0 ohm means we actually need a short circuit like this. So, no extra resistance is required, meter resistance itself is enough. Okay. So, this is how we can change the range of a voltmeter, and we can also make multi-range voltmeters. Now, the important thing that we should talk about voltmeters is this. Okay. So, voltmeters, firstly, this is a trivial fact. Voltmeters are connected in parallel to the unknown voltage. Okay. So, if I have a unknown voltage source and I want to measure the voltage of this, I have to connect the voltmeter V across this like this. So, this is the symbol of a voltmeter, a V inside a circle. If I have a complicated network, maybe like this, and say I want to measure the voltage across this resistance. Okay. I want to measure the voltage between these two terminals, then I have to connect the voltmeter V in parallel to this resistance. Okay. So, this is always connected in parallel. Okay. So, then okay. So, here this V, if I call this E, then this voltmeter V measures E. In this circuit, if I call this potential drop as, call this as V1 between these two terminals, then this voltmeter is measuring voltage V1. Okay. So, voltmeters are always connected in parallel to the unknown voltage that we want to measure. Now, there is a problem. What is that problem? The problem is that okay, so the voltage, the unknown voltage that we want to measure may get changed when we connect a voltmeter across it. Okay. So, why that is so? Because the voltmeter has some internal resistance, therefore, in this circuit some current will flow now through the voltmeter as well, which was not flowing previously through this previously when the voltmeter was not there. Now, some extra current is flowing through this. So, the circuit is changed because of this voltmeter, and therefore, this voltage may change when you connect a voltmeter. So, let us take some small example. Okay. So, example, Okay, so let's take a simple battery just like this with some internal resistance Ri. Okay, so this is a battery with EMF E and Ri is the internal resistance of this battery. So this is a battery or cell, a voltage source. Okay, so now what is the EMF between these two terminals? This should also be equal to E. Okay, so the potential difference between these two terminals is E. But now if we want to measure the value of this potential difference using a voltmeter, so we have to connect a voltmeter between these two terminals like this. So this is a voltmeter, and say the internal resistance of this voltmeter is Rm, Rm for meter resistance. Now the question is, what will be the reading of the meter? So what will be the reading of this meter? So we know in the absence of this voltmeter, this potential difference was E. But will this voltmeter indicate that value E, or will it indicate some other value? Okay, so let's compute that. So the answer is very simple. Okay, so if I connect this voltmeter, then the current that flows in this circuit I, this is given by, this is E divided by Ri, internal resistance of this source battery, plus Rm. And if so, then the voltage drop across this voltmeter, so V, that is the voltage drop across the meter, okay, this will be this current I multiplied by Rm, Ohm's law. Now in place of I we write E by Ri plus Rm, and then this is multiplied by Rm. Okay, you can also write it as E multiplied by Rm by Ri plus Rm, and this is not equal to E, right. So the voltmeter reading will not be same as the voltage that was there before the connection of the voltmeter. Okay, so we can have some error. Now when, okay, so now how much is the error? So the error we can write, say, the percentage error or relative error. So this we can write as, say, the true value, which is E, multiplied by the meter reading, which is E Rm by Rm plus Ri. So this is the true value minus the meter reading divided by the true value. Let me take it as the true value. Okay, so this we can write as E cancels. So I will have 1 minus Rm by Rm plus Ri. So this will be equal to Rm plus Ri minus Rm. So this will be Ri by Rm. When will this value be low? Now to have a low error, low percentage error, okay, we need Ri by Rm close to 0 or Ri much less than Rm, okay, or Rm much greater than Ri. So, this is the requirement. What is the requirement? The voltmeter resistance, the meter resistance Rm should be very large compared to the resistance of the internal resistance of the source. Then only our reading will be correct. Okay. So, therefore, ideally a voltmeter should have infinite, theoretical infinite, practically very large resistance. Okay. So, this is one important fact about the voltmeters that you should know. And now, in this example, we have taken a very simple circuit, okay, just a battery with an internal resistance. What will be the case if we use a complicated circuit where we want to measure a voltage? So, even if we take a complicated circuit, even if we have a complicated circuit, complex circuit, okay, say like this, let us take a complex circuit. And say we want to measure the voltage across this terminal. Okay. So, we have to then connect the voltmeter here. Okay. Now, what should be the value of the Rm? It should be high, but how high? Once again, even if we have a so complicated circuit like this, by virtue of Thevenin's theorem, we can always simplify this circuit into its Thevenin equivalent. So, we can always find the Thevenin equivalent as long as the circuit is linear. So, Thevenin equivalent circuit from the view of the voltmeter Okay, so, this is important from the view of the voltmeter, that means from the view of the terminals where this voltmeter is connected. That means, if we look into this circuit from these two terminals, from the perspective of these two terminals, so we can always get a equivalent voltage source, call it VTH, Thevenin voltage, in series with RTH, Thevenin resistance. This is same as the Norton's resistance, okay, and the voltmeter is here with internal resistance Rm. Now, we can say Rm should be much higher than RTH, Thevenin resistance, that is the resistance of the circuit as seen by the voltmeter. So, this is what we want. Thank you.